Hello everyone, the project I did was CartPole LQR control analysis. I'm going to present my project in three sections. The first is I will describe the CartPole control problem and derive the motion equation. This is the most challenging part. And then I will design a linear quadratic regulator. And the last part is the real-time simulation, and I will compare the effect of R matrix and Q matrix. The CartPole problem can also be called inverted pendulum problem because it's composed of a cart and a pole, and the goal is to move the cart to the designed position while keep the pole balanced. The physical CartPole model is shown below. The state we used is x dot, theta, and theta dot, where x is the position of the cart, while the theta is the pendulum angle from the vertical line. First, let's look at the cart. From the Newton's second law, we can get that u minus dx dot minus t sine theta equals to m times the acceleration of the cart. Then if we look at the pole, horizontally and vertically we can derive these two equations, but we don't know the AI and AJ. In order to get AI and AJ, we need to calculate the acceleration of the pendulum, and it has three types of accelerations at different directions. But if we decompose all of them at I direction and J directions, we will get AI and AJ as shown in Formula 4. By using all of those above equations, we can get the dynamics functions of x dot and theta dot. And we can see this clearly that it is a nonlinear problem, so we need to linearize it. When theta is small, we can approximate cosine theta to be 1 and sine theta to be theta, and theta dot square equals to 0. And if we plug in this approximation to the previous nonlinear model, we can have this new linear model, which we will get the matrix A and matrix B. Then we go to LQR controller design. LQR controller has a cost function to minimize, and it has the Q matrix and R matrix. The Q matrix will punish the difference between the current state and the reference state, while the R matrix will punish the input we added to the system. In MATLAB, we can just run this one line to get the LQR controller. So let's go to this real-time simulation. For the setup, the goal is to move the cart from position -3 to 3 while keep the pole upright. For the first simulation, when we choose the diagonal value of the Q to be 1 and R to be very small, the cart took 7.1 seconds to achieve the target and use 14 units forces. And for the second simulation, if we increase the R, the controller becomes less aggressive, while it took much longer time to converge, but it uses only 3 units of forces. For the third experiments, we increase the punishments of the position error, and we can see it only took 4.6 seconds to converge, but it used 24 units of forces. Then we can get the effect of the R matrix. If we increase the R, less forces will be applied on the system. That is because we have a higher cost of the forces. But the cost is that we will take much longer time to achieve the target. We can also get the effect of the Q matrix. If we increase the penalty for the position error, then we will use much less time to get the target position. But we will use more forces because this is more aggressive control. So The advantage of LQR controller is that we can get different controller based on the criteria we care about. Thank you.